This mini-lecture reviews the terminology and stoichiometric relationships of acid-base titrations, and titrations in general. Titrations are a volumetric analysis technique that uses the stoichiometric mole ratio in a reaction to determine the unknown concentration of a solution. This is done by reacting the solute in the solution of unknown concentration with another solution that contains a different reactant but with a known concentration. So, each of these two solutions contains one of the two reactants that generate a chemical reaction when mixed together. This technique can be used for many different types of reactions, but the terminology is the same no matter what type of reaction is being conducted. The solution of known concentration is called the titrant, and this is the solution that is loaded into a special piece of glassware called a burette, or burette. The burette provides a way to measure the amount of solution that is delivered into the reaction flask with high precision. And it can also deliver the titrant drop by drop, giving careful control over the amount of titrant that is added to the reaction flask. In any given titration experiment, the amount of titrant that needs to be added to the reaction flask to complete the reaction will depend on the moles of the titrant solute that are needed to fully react the moles of the other reactant that is present in the reaction flask. At any point during the reaction, the moles of the titrant solute, N, can be determined from the known concentration, M, of the titrant, and the volume of the titrant that has been added to the reaction flask, or V. The solution of unknown concentration that contains the other reactant is called the analyte, and this is the solution that is already present in the reaction flask before adding any titrant, so before the titration is started. To determine the unknown concentration, M, of the analyte, the moles of analyte solute, N, contained in the volume of the solution, V, must be known. The volume of the analyte is carefully measured when adding the analyte to the reaction flask and before the titration begins. So, if the volume is known, then the goal of the titration is to determine the number of moles of analyte solute that are contained in this original volume of analyte. To do this, the reaction between the titrant and analyte reactants must be known, so that the stoichiometry or mole ratio between these two reactants can be used to determine the moles of one reactant based on the moles of the other. So, since the moles of the titrant can be determined from the known concentration and the volume added, then the moles of the analyte can be determined based on the mole ratio between the two reactants in the reaction. However, in order for these calculations to work, the reaction must be conducted with the exact stoichiometric amounts that are required so that both reactants are completely used up. In other words, there shouldn't be a limiting reactant and there shouldn't be any leftover excess reactant. The amounts of both reactants must be just right. This perfectly matched point for the reaction is referred to as the equivalence point. And when the titration experiment utilizes an acid-base neutralization reaction like we've seen before, where the stoichiometric ratio between the acid and base reactants is 1:1, this means that the moles of the acid and the moles of the base in the perfectly balanced reaction will be equal. So as long as we can calculate the moles of one of these two reactants at the equivalence point, we can then calculate the moles of the other. But how will we know when the equivalence point has been reached if we don't know how much of the analyte reactant is in the flask to begin with? How will we know how much titrant to add so that we are providing enough to fully react the analyte without adding excess titrant? For this, we need an indicator, something that will give a visual cue for when the reaction has reached the equivalence point. In acid-base titrations, the indicator is often a chemical called phenolphthalein, which will change color when the equivalence point has been reached, indicating that the exact amount of titrant needed for a perfectly balanced reaction has been added. At this point, we stop adding the titrant and measure the volume of the titrant that was added to reach that equivalence point. This volume of titrant is then used along with the known concentration of the titrant to determine the moles of titrant that reacted, and therefore the moles of analyte that were originally in the reaction flask. Okay, let's do an example by considering the titration of an unknown concentration of hydrochloric acid with 0.5 molar sodium hydroxide. For clarity and dramatic effect, I've color-coded the two solutions green and orange, but keep in mind that both of these solutions would actually be colorless in reality. The sodium hydroxide solution is the titrant because it has a known concentration of 0.5 molar, and this solution is added to the burette as shown. The hydrochloric acid solution is the analyte because its concentration is unknown, and this solution is added to the reaction flask, which will be positioned below the burette when we're ready to start the titration. The original volume of the analyte is always known, and in this example, 295 milliliters of this hydrochloric acid analyte have been added to the reaction flask. So, this means that the goal of this titration example is to determine the number of moles of hydrochloric acid that are contained in the 295 milliliters of analyte, so that we can calculate the molarity of the analyte by simply dividing the number of moles by the total volume of 295 milliliters. Now, the neutralization reaction between hydrochloric acid and sodium hydroxide is a reaction we have seen before, and we know that they will react in a 1-to-1 mole ratio based on the balanced reaction that we've shown here. So, for every 1 mole of hydrochloric acid in the reaction flask at the beginning, 1 mole of sodium hydroxide will need to be added to reach the equivalence point. To detect when the equivalence point has been reached, we add a few drops of that phenolphthalein indicator to the analyte in the reaction flask. Phenolphthalein is colorless in acidic solution and pink in basic solution, so when it is initially added to the acidic analyte hydrochloric acid solution in the reaction flask, the solution will remain colorless. So excuse the orange color that I've shown here, just ignore that, because I've really just done this to show that this is the analyte solution. In reality, this would be colorless, even with that indicator added in. Now, during the titration, when the equivalence point is reached, the analyte will rapidly turn pink, signaling that the reaction is complete and the titration should be stopped. Again, we know based on this 1-to-1 ratio in the reaction that at the equivalence point, the moles of hydrochloric acid that we started with in the reaction flask will now match the moles of sodium hydroxide that have been added to the reaction flask from the burette. So, we are now ready to begin the titration. The reaction flask containing the analyte is positioned beneath the burette containing the titrant. The stopcock on the burette is slowly turned to start the titrant drip into the reaction flask. As the titrant drips into the analyte, the volume inside the burette is monitored as it slowly decreases. When the solution turns pink, the stopcock is closed, stopping the slow drip of the titrant. When the solution turns pink, the equivalence point has been reached, and we are ready to analyze the results. So, how many moles of sodium hydroxide were added to reach the equivalence point? To determine this, we need the volume of titrant that was added to the reaction flask in the titration. This can be determined by subtracting the initial reading on the burette from the final reading on the burette. The titrant solution started at 0.00 milliliters, and to reach the equivalence point, it was drained to 4.00 milliliters. So we take the final reading of 4.00 milliliters, subtract the initial reading of 0.00 milliliters to solve for the volume added as 4.00 milliliters. Note that the markings on a burette are such that the final reading will equal the volume added if the titrant solution starts at the 0.00 milliliter marking at the top of the burette. So, to find the number of moles of sodium hydroxide that are contained in this 4 milliliters of titrant that were added, we use the known molarity of the solution of 0.5 molar as a conversion factor. Starting with the 4 milliliter volume, converting it into liters, and then using the molarity as a conversion factor of 0.5 moles of sodium hydroxide per 1 liter of solution gives 0.002 moles, or 2 times 10 to the negative third moles of sodium hydroxide that were used to reach the equivalence point. So that means that 2 times 10 to the negative third moles of sodium hydroxide were needed to perfectly neutralize the amount of hydrochloric acid we had in the flask to begin with. Okay, then how many moles of hydrochloric acid were in the flask originally? If we know that 2 times 10 to the negative third moles of sodium hydroxide were added to reach the equivalence point, then we know based on the 1-to-1 mole ratio of the neutralization reaction that the same number of moles of hydrochloric acid were present in the reaction flask at the beginning. So this means there were 2 times 10 to the negative third moles of hydrochloric acid in the original analyte. Okay, then what was the original concentration of the analyte? For this, we need to remember that 295 milliliters of the analyte solution was added to the reaction flask initially. So if that volume of analyte contained 2 times 10 to the negative third moles of hydrochloric acid, then we solve for the molarity by dividing the moles of hydrochloric acid by the total volume of the original analyte solution that was titrated. This gives an analyte concentration of 6.78 times 10 to the negative third molar for the original analyte solution. Now, titrations are usually covered pretty thoroughly in the general chemistry lab classes, but we're covering this concept in lecture just to make sure that everyone is prepared for problems set in the context of a titration experiment. These are really popular for stoichiometry problems because it allows you to apply some of the knowledge we're learning in lecture to a practical situation that we often see in the lab. So keep in mind that titrations are just a special type of stoichiometry problem. And the main thing you should be focusing on is recognizing the terminology that is used in this situation and how it applies to the stoichiometric calculations that are required for such problems. So make sure you know what the terms titrant and analyte refer to, and what is implied by the equivalence point, so that when you encounter a problem that gives you the volume of titrant that was used to reach the equivalence point, you'll now know how to use that information to solve for the concentration of the analyte. Or you may encounter a problem that asks you to work in the reverse direction and instead calculate the volume of titrant that will be needed to reach the equivalence point for a given amount of analyte. There's lots of different ways these types of problems can be phrased, so make sure you understand the context of these types of experiments so you're prepared for those types of word problems. This concludes the fourth and final mini lecture for material from Chapter 9 and the material that will be on midterm number 4. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.